Got a physics exam on vectors coming up? Don't even sweat it. In just the next few minutes, we're going to fly through the absolute essentials you need to know. The goal? To have you walk into that test feeling totally confident. So let's get right to it.
All right, let's start with a simple thought experiment. Imagine you walk 9 blocks east, and then you take a left and walk 5 blocks north. Now sure, you've walked a total of 14 blocks, but how far are you really from where you started? What's that direct, straight-line path back to your front door? Well, that question is a perfect job for vectors. Keep this problem in your back pocket. We're going to solve it in just a little bit.
But before we can find that shortcut, we have to get one really fundamental concept straight, and that's the difference between scalars and vectors. It might seem like a small detail, but trust me, it's the foundation for everything else we're going to talk about. So, on one side, you've got scalars. These are super simple. They're just a number, a magnitude. How hot is it outside? 20 degrees. How fast is the car going? 10 meters per second. Easy. But on the other side, we have vectors. And vectors have a little more information packed in. They have that magnitude, that number, plus the direction. So it's not just 10 meters per second, it's 10 meters per second north. The key takeaway here? The only thing that separates a scalar from a vector is direction. That's it.
Okay, so how do we actually add our 9 blocks east vector to our 5 blocks north vector? The easiest way to picture this is with something called the head-to-tail method. Let's break down how it works.
But first, some really quick vocab. Every vector, which we draw as an arrow, has 2 ends. The starting point is called the tail, and the pointy end, the arrowhead, that's called the head. Simple enough, right? The tail is where you start, and the head is where you're going.
The whole process is actually kind of like following a treasure map. First, you draw your first vector, your first part of the journey. Then, right where that one ended, at its head, you start the next one. You just keep chaining them together, connecting the start or tail of each new vector to the end or head of the one before it. Once you've laid out all the parts of your journey, the final answer is just one single vector drawn directly from your absolute starting point to your absolute ending point.
Theory is one thing, but let's make this real. Let's go back to our city walker problem and actually build the solution step by step.
Okay, first things first. We draw our first displacement vector. It's just an arrow that represents our journey of 9 blocks to the east. A simple, straight line. Now here comes the key move. We apply the head-to-tail rule. We take the tail of our second vector, the 5 blocks north one, and we plant it right on the head of that first vector. See how they connect? It's like one continuous path.
And finally, we draw our answer. This is the big one. It's the arrow that connects our original starting point, the tail of the very first vector, all the way to our final destination, the head of the very last vector. This new vector is that shortcut we were looking for.
And here is our final answer. If you were to measure that shortcut arrow, you'd find its length is about 10.3 blocks. That's our magnitude. And if you measured its angle, it would be 29.1 degrees north of east, and that's our direction. Now, you could also get these exact numbers using the Pythagorean theorem and a little trigonometry, but the visual method shows us the very same result.
That final answer, that shortcut vector, has a special name. We call it the resultant. It's just a fancy word for the sum of all the individual vectors. It shows the net result of the entire journey, from your absolute start to your absolute finish.
Now here's a really cool and important property of vectors. The order you add them in doesn't matter one bit. If you had walked north first and then east, guess what? You'd end up in the exact same spot. Your final resultant vector would be completely identical. This is called the commutative property. A plus B is the exact same thing as B plus A.
So, we've totally nailed addition, but what about other things we can do with vectors? Let's really quickly cover 2 more essential skills, subtracting vectors and multiplying them. Well, I've got some great news for you. You basically already know how to subtract vectors. It's not really a new skill, it's more of a clever trick. To subtract vector B from vector A, all you have to do is add the opposite or the negative of vector B to A.
So what is a negative vector? It could not be simpler. It's a vector with the exact same length, the same magnitude, but it's been spun around 180 degrees to point in the complete opposite direction. That's literally it. And finally, what happens when you multiply a vector by a regular number, a scalar? Well, if you multiply by a positive number, like 3, the vector just gets 3 times longer, but it keeps pointing the same way. But if you multiply by a negative number, like -2, 2 things happen. It gets twice as long, and it flips around to the opposite direction.
Okay, deep breath. We've covered a lot of ground pretty fast. So let's boil it all down to the absolute must-know essentials that you need to lock in for your exam.
All right, this is it, your final exam checklist. First, scalars are just a number, but vectors need a number and a direction. Second, we add vectors visually by chaining them together head to tail. Third, that final shortcut vector, the overall result, is called the resultant. And fourth, subtraction is just a trick. You add the opposite. If you can remember these 4 points, you are going to be in great shape for your test.
So I'll leave you with this final thought. We've been talking about just walking around a city. But how could you use these exact same rules, adding vectors head to tail, finding resultants, to understand something way more complex, like all the forces of lift, drag, thrust, and gravity all acting on a moving airplane at the same time? Because that's where this stuff really starts to get powerful.